Hello everyone, my name is Karan Bhagat.
And I am Jatin C. from CMR Institute of Technology. Under Emertxe, we have done an implementation of a washing machine using a PIC-GNS board.
Okay, so before we start out with the project, I would like to first give a glance about what the microcontrollers and what embedded systems actually are. So microcontrollers are integrated circuits which are capable to be programmed to perform a specific task. So the design normally has restrictions on its memory size, capabilities, and peripherals as they are very small. Okay, so there are many microcontrollers available in the market. So how do we choose a microcontroller? So we choose a microcontroller based on the following criteria, that is application, performance, price, and availability. Now, what is embedded systems? Embedded system is basically a combination of hardware and software which is intended to do a specific task. There's a lot of comparison between embedded systems and a GPS system. So a GPS system is basically used to perform a large number of tasks. So there are many types of embedded systems, namely standalone systems, real-time systems, network systems, and mobile systems. So under standalone systems, there are two types, slave systems and independent systems. So slave systems are not intelligent and the system cannot actually take action by themselves. For example, a semi-automatic washing machine. Independent systems can take actions on this by themselves. Example, the Google car, which is basically driverless car. Um, Now, coming under real-time systems are basically time-bound systems, and whatever action takes place in these systems will take place in a specified time. And failures in these systems are not acceptable. For example, an airbag system. Next comes the network systems. These systems are basically connected to a large network, for example, an home security network. Mobile systems. These systems are basically movable, for example, robots. Now we come under look at the embedded system components. So there are many components of an embedded system. This is basically a microcontroller which has many functions, which has many utilities such as a digital to analog converter, analog to digital converter, a memory, and many other sensors are basically connected to this microcontroller. And these all the hardware components are then again what is that interfaced with a software, and this as a whole forms an embedded system. So for this project, we've basically followed a five-step process. This is basically first step is requirements, then comes the analysis, then the design and development, and finally the implementation. Requirement analysis. Purpose. The purpose of this project is basically to develop a washing machine. A washing machine is basically an home appliance which is used to wash laundry, and it also has a variety of washing modes. Functional requirements. So the project which we are going to do is going to have 12 programs. Daily, heavy, delicate, white, stain wash, sari, woolen, bed sheets, rinse plus spin only, wash only, and aqua store. Each of them have four different water levels: low, medium, high, and very high. And the times for which the washing machine will operate is specified in this table, which you can see. Next comes the analysis. So this is how a program is going to proceed. This is going to be our main screen. So basically we press key 5, that is the RB4 in the PIC genus board. Once we click RB4, this is the powering on screen, which stays for approximately 3 milliseconds. After the screen gets over, next we have the different types of washing modes, such as daily, heavy, and delicate. To select a mode, we have to long press the RB3 key. After we select the washing mode, we then have to select the water level. Again, similarly, we need to long press RB3 to select the water mode. After that, we have two options, that is start and stop. Clicking RB4 will then start our washing machine. The next screen basically shows the type of washing mode, the time, and also gives us an option to start as well as pause. There's an option to open the door. RB0. In this case, the buzzer will also beep, and once the washing is done, this is our final screen which pops up. Okay, so next comes the software requirements. So we have MPLab XID, PixMLab, and XC8 compiler. So MPLab is basically a proprietary freeware integrated development environment for development of embedded applications on PIC microcontrollers. So the MPLab latest version is built by Microchip Technologies and is based on open source NetBeans platform. Um, Pixim is basically a real-time emulator of development boards with which is also integrated to MPLab X. Pixim Lab supports Pixim microcontrollers and some other various microcontrollers. Um the MPLab XC8 is basically the C compiler for 8-bit PIC and other devices. Design and development.
So in design and development, first we look at our microprocessor and the microcontroller. So the microcontroller we'll be using is the PIC Genos. So this is the general architecture of the PIC Genos board. So it has a central microcontroller, a PIC 16F877A, and there are a lot of other peripherals connected to it like LED, buzzer, SSD, CLCD, sensors, switches, and keypad, and a lot of these. For our project, we'll be making use of the buzzer, the keypad, CLCD, a few switches, a few interrupts, timers, and etc. If needed, we can even attach it with a motor or something else to simulate the washing machine. So the PIC16F77A microprocessor, it can operate up to 20 megahertz frequency. Operating voltage is about 4.2 to 4.5. It does not have an internal oscillator. The max current is 1000 milliampere. It's an 8-bit microcontroller with 40 pins. It has multiple registers which can be controlled, which can be inputted to change the status of the microprocessor, such as status register, tris registers, etc. The micro the board has 6 ports: port A, B, C, D, and E. Port B to D are 8-bit ports. Port A is your 6-bit port, and port E is your 3-bit port. The tris register can be inputted high or low. Depending on that, the ports will either be an input port or an output port. The bus width of this microprocessor is 8 bits. CPU speed is around 5 milliseconds. RAM size is 386 bytes, and EEPROM size is 256 bytes. Like I said, it has 3 timers, I2C, UART, ADC, SSP, and all other devices needed. So CLCD. See, we'll be using CLCD to mainly communicate with the user. Whatever we want to display, we display on the CLCD. Pixim comes with 2 versions of CLCDs. One is a 16 into 4 CLCD, and one more is a 16 into 2 CLCD. We'll be making use of the 16 into 4 CLCD. So CLCD stands for liquid crystal displays, and each block can display a different ASCII characters. And to select the required ASCII characters, we input it with either 8-bit or 4-bit control. So depending on the control signal, we can select what character gets printed. Tactical switches. So tactical switches they're used in a variety of places. These are switches which respond to touch. So they are like a pulsating switches. Every time you press, you get one signal. So tactical switches are also used in your phone for power on and off. We'll be using it in a similar fashion for power on and for changing through different operating modes. These are switches which are perceived by touch. These switches are used to select all the different modes. Okay, so when selected, sometimes these switches, because of how they're constructed, produce a bouncing effect. We deal with such abnormalities in the code by increasing the delay of how we accept data. So there are 6 of such switches on the board. So SW1 to SW6, these are connected from RB0 to RB5. 3 out of these switches also act as interrupts. We'll get to that later. There are 2 fashions in which these switches can be uh, fashioned on the board. One is called a pull-up register circuit. One was called a pull-down register circuit. On board, we'll be making use of a pull-up resistor circuit. Okay, there's an other part of the board where these tactical switches are arranged in a grid-like structure to form a keypad matrix. This can be used to type out numbers, different combinations, and because of their grid-like structure, they make use of less connections. Interrupts are important. So suppose your program is running and suddenly you want to stop it to service another more important program. So interrupts can be used then. So when an interrupt is pressed, your control goes back and attends to the service which is being requested right now. Once that program is completed, the interrupt control comes back to the program which is stopped, so it completes that program. We use interrupts here in our project to simulate the opening and closing of the door of the washing machine. And in the board, we have three interrupts. In the board, we have three interrupts connected from switch 1 to switch 3. So basically RB0, RB1, and RB3. Timers. Timer is basically a peripheral in embedded systems which is in control of all the timing and clock. So there's a few technical terms when it comes to timers. So tick is the basic instruction cycle of your processor. Resolution is the length of the counter which we use to make the timer happen. And then quantum is a period of each tick. Scaling can be used to change your length so that we can fix the timer so that it ticks out after every second or 2 seconds or such. In our board we have three timers: timer 0, timer 1, and timer 2. Timer 1 is an 8-bit timer slash controller. Here interrupt happens every time the counter overflows from FF H to 00H. We have timer 2. Timer 2 is a 16-bit timer. Timer 3 is an 8-bit timer, but timer 2 is an 8-bit timer. And the thing about timer 2 is it also comes with an register called PR2. The PR2 register can be set to any value between 00H to FFH. So the timer starts counting from 00H till the value of the PR2 register, and once it's done, it overflows back to 00H. And every time it overflows is an interrupt occurs. So we can use timers to count. We can also use timers to run interrupts. Next slide. So now we go on with the implementation. In this, I'll talk a few things about the board, and then we can go ahead. So here, this is the CLCD display on the green, and here RB2, RB, RB1, and RB0. These are your interrupts. So INT1, INT2, and RB5, RB4, and RB3 combined with RB0, RB1, and RB2 form our tactical switches. We have a buzzer, we have a fan. The fan will be used to simulate the DC motor. If needed, we can also interface this board with the DC motor to run the DC motor. Now Karan will go ahead with the simulation.
Okay, so as you can see that this is a starting screen. Press key 5 to power on the washing machine. So RB4 is basically a fifth key. So once we click the RB4, you can see the washing machine has been powered on. Now we get various modes to select. For this demonstration, I will just be choosing the daily washing mode. So for choosing the daily washing mode, what I need to do is long click the RP3 button. As you can see now, we have selected the daily washing mode. Now we have an option to choose the water level, which is auto, low, and medium. Again, for this demonstration, I will be choosing the auto water level, and for choosing that I will again have to long press the RB3 tactical switch. Okay, so now we have the option to start our washing machine. So I'll be pressing the switch 5 to start our washing machine. Okay, so here we can see that The mode we have selected is daily. The time taken for a daily wash is basically 41 seconds. We can start and stop the washing machine using switch 5 and switch 6. For demonstrating, I clicked switch 6, which has then paused the washing machine. Uh, Yeah, the washing machine's paused now. And now I will press switch 5 to again start the washing machine. We can also use the RB0, which is an interrupt, to basically open the door. It takes 26 seconds for this wash to complete. I'll fasten up the timer by increasing the clock so that the operation gets over faster. The washing's done, and this is a final message which is displayed. Now we come back to our washing modes again. Thank you.
Thank you.